Hi, my name is Ravi. Welcome to my channel, Payment Talks. Welcome to the Packsite Masterclass series. Over 8 parts, we are going to take the ISO 2022 Packsite customer credit transfer apart completely. Not just the XML, the life cycle, how it is initiated, how it is created, how it travels, how banks process it, and how you build systems that handle it in production. This is part 1, and we are going to start somewhere that most people do not start before the message exists. By the time a pack set exists, the hard work is already done. That is the foundational insight of this entire series. Most teams start learning pack set at the XML. They open the schema, they look at the fields, they immediately miss the most important part of the story. Because by the time the XML exists, the bank has already done enrichment, compliance screening, limit checking, routing, settlement date calculation, charge bearer determination, and UETR assignment. The pack set is the conclusion of a process. It is not where a payment begins. It is where an enriched, validated, approved instruction finally becomes a network message. If you start at the XML, you are starting at the wrong end of the story. Let me give you a concrete example that we will carry through every single concept in this video. Meet Claudia. She is the corporate treasurer at a manufacturing firm in Munich. Today, she needs to pay her Italian supplier for a batch of parts delivered last month. The supplier is Acme Engineering, based in Milan. The invoice is invoice this number. The amount is euro 50,000. She has the supplier's IBAN. This. The purpose reference is invoice. Value date today. She logs into her company's corporate banking portal. She fills in the payment form. She hits submit. What happens next has absolutely nothing to do with XML. At the moment Claudia hits submit, the bank has received exactly three things: her intent to pay euro 50,000, the creditor identity and IBAN, and the remittance reference invoice. That is it. What the bank has not yet done is substantial. No enrichment has happened, no compliance screening has run, no routing decision has been made, no UETR has been assigned, no pack set exists. What the bank has is an instruction that needs to be processed, not a payment that has already been made. Before we talk about formats, channels, or system architecture, we need to establish something fundamental. What is customer intent and why does it matter so much? Here is the most important sentence in this video. Whatever the customer provides as intent, the bank does not change it. Once the customer has told the bank what they want to do, the bank's obligation is to carry that intent unchanged through the entire payment lifecycle. These are not fields to enrich. They are not fields to modify. They are not fields to calculate into. They are the instruction itself. And if your system touches them after intake, that is a design defect. Now, let me map Claudia's payment onto those 9 elements. Data identity, Munich manufacturing firm with her bank's BIC. Creditor identity, Acme Engineering, the IBAN is given. And the creditor bank BIC that the bank will derive from the IBAN. Instructed amount, euro 50,000 exact. Currency, euro. Pre-agreed FX rate, not applicable, same currency on both sides. Value date, today. Purpose code, not provided in this payment. Remittance information, invoice number. Urgency, not specified. All 9 captured. All 9 sealed into layer 1 of the canonical instruction at intake. That is part 1's first deliverable. Customer intent has to reach the bank somehow, and the way it arrives varies enormously. Let me show you the 9 main channels through which customer intent arrives at a bank today. A corporate treasury system like SAP Treasury or Kiriba sends Payno1 XML directly. An open banking or REST API delivers JSON or XML, usually Payno1 aligned. ERP systems from SAP, Oracle, and similar vendors use proprietary formats or Payno1 exports. Mobile and web portals receive HTML form submissions. E-forms and web applications send JSON over HTTP post. Excel and spreadsheet uploads come in as XLS, XLSX, or CSV files. Host to host connections deliver empty messages, CSV, fixed width files, or Edifact. Branch systems use teller form entry that maps to core banking fields. And legacy Swift MT103 is still alive in many production environments today. 9 channels, 9 different packaging formats, 1 customer intent. This list is illustrative, not closed. New channels get added as payment ecosystems evolve. Where does Claudia sit in this landscape? Her company uses a corporate banking portal. That means HTML form over HTTP post. At no point has Claudia produced Payno1 XML. She filled in a form. The bank's intake layer maps those form fields to the Payno1 logical structure. The same intent, different packaging. The bank's job is to normalize that packaging into a single internal working format, regardless of which channel it arrived from. This is where I want to address the single most common confusion I have encountered in payment system teams. Here is a conversation I have seen happen on almost every payment project I have worked on. The business analyst says we process Pain1. The developer says we use an API. Both of them are right. Both of them are confused about why the other person seems to be describing something different. This is not a communication failure. It is an architecture gap. They are talking about two completely different dimensions of the same system. And until the team names that distinction explicitly, it keeps causing problems. The developer is talking about format. Format is a transport layer. It is how the data physically moves from one system to another. REST API delivering JSON, XML over SFTP, SwiftFin MT103, CSV file upload, Excel spreadsheet, HTML form post. These are all formats. They tell you how the bytes travel. They say absolutely nothing about what the data means. Structure is the semantic layer. It tells you what the data means. ISO 20022 Payno1 is a structure. It defines a group header, a payment information block, and inside that block, DETAR, a credit transfer transaction block, and inside that block, creditor, the instructed amount, purpose, and remittance information. This structure exists regardless of how the data is transported. You can deliver Payno1 structure inside JSON, you can deliver it inside XML, you can map it from a CSV. The structure describes the meaning, the format describes the transport. Here is the resolution. We use REST API, that is the format. The payload is JSON, that is the encoding. The data is Payno1 organized, that is the structure. 3 words, 3 different dimensions, all simultaneously true. When the BA says Payno1, they mean the structure. When the developer says API, they mean the format. Both correct. Now name it explicitly in your architecture documents from day one and watch months of confusion disappear. If you do not name this distinction, your parsers get hard coded to a format. The next channel arrives. The parser does not know what to do with it. What should be 2 weeks of adapter work becomes a 2 month rebuild. Now that we understand the channel and format problem, let me answer the question every BA asks when I propose adding a canonical layer. The question is, why not just map Payno1 directly to Paxo 8? We have the ISO mapping tables. Why add a canonical layer? Start with CBPR plus cross border. Build a direct mapper. It works. Now add SEPA SAT, different charge bearer rules, different settlement method, different remittance limits. Add conditional logic to the mapper. Now add domestic RTGS, more conditionals, more branching. The mapper is getting harder to read and harder to test. Now add instant payments, scheme specific validation, real time constraints. The mapper is now a maze. Every scheme adds more conditional branches to the core engine. Every regulatory change risks breaking the logic for another scheme. Debugging a failure in production means tracking through all of that. And the failures are not always loud. Sometimes the wrong value makes it into the PAX 8 silently. The canonical instruction solves this cleanly. Without canonical, customer data is mixed with scheme logic inside the same mapper. New scheme means touching the core engine. Channel format diversity is baked into the parser. Every change creates cascading risk across the whole system. With canonical, customer data is sealed in layer 1 and never touched again. Scheme specific rules operate on layer 2 only. A new scheme means building one new adapter that populates layer 2 differently. The core engine does not change. One engine, one canonical structure, multiple scheme adapters. That is the architecture that scales. I built a CPPR plus canonical. From the beginning, it was designed as a superset, not just the fields needed for the single scheme today, but the full set that any scheme might need in the future. When we began onboarding new rails like SEPA, Links, and others, the fields were already in the canonical. They had been sitting there empty, waiting. The work was building a Links, SEPA, or any other scheme adapter, which populated those layer 2 fields differently to how the CBPR plus adapter did. The payment engine did not change, not one line in the core engine. That is a proof of the superset design principle in a live production system. If you design your canonical for the scheme you have today, the scheme you add tomorrow forces a scheme migration that touches every downstream service simultaneously. Design it as a superset from day one. Now, let me show you how the canonical functions inside the payment engine in real operation. Think of the canonical instruction as a hub of a wheel. The compliance service connects to it. It reads the debtor, creditor, and ultimate party fields from layer 1. It runs its screening. It writes the clearance status back to layer 3. The enrichment service reads customer fields from layer 1, runs big lookups and regulatory data checks, writes the results to layer 2. The routing engine reads the enrichment results from layer 2, selects the correspondent and settlement method, writes those decisions to layer 2. The limit check reads instructed amount from layer 1, runs the check against daily aggregate, writes the result to layer 3. UETR assignment reads the compliance clearance status from layer 3, confirms it as cleared, generates the UUID and writes it to layer 2. The PAX8 generator reads the fully populated canonical and produces the message. No service receives the original channel format. No service touches a half-built PAX8. On the input side, 6 different channels formats arrive through their own input adapters, each mapping to the canonical. New channel format, one new adapter. Nothing else in the engine changes. Let me make the architectural difference concrete. With canonical architecture, a new mobile app sends JSON payments. You build one input adapter that maps that JSON to the canonical instruction. The canonical is unchanged. All 6 processing services are unchanged. The PAX8 generator is unchanged. One new component, everything else untouched. With the direct mapping architecture, the same mobile app JSON arrives. Now you need to update the mapper to handle JSON input structure. You need to update the validator because its input assumptions change. You need to update the generator because the mapper output has changed. Three simultaneous changes to three components that share production risk. Canonical is extensible by design. Direct mapping is extensible by effort. That is the fundamental architectural difference. Now, let us look inside the canonical. What is in it and how is it organized? The canonical instruction has three distinct layers. Layer 1 is the customer core, that is pay no one aligned. It holds everything the customer provided as intent. It is sealed at intake and never modified. When the pack set is generated, layer 1 fields flow into it unchanged. Layer 2 is bank enrichment. This holds bank generated and derived fields UTR, settlement method, charge bearer, creditor agent BIC, intermediary agent BICs. At the end of part 1, layer 2 is entirely empty. It fills during part 2. Layer 3 is internal metadata. This is the engine's operational state. Intake timestamp, validation status, compliance clearance, routing record, batch metadata, retry count, error log. And critically, layer 3 never flows into the packset. It is the engine's working memory, not message content. Layer 1 holds the 9 customer provided elements we covered earlier. Debtor identity, name, account number, their bank. Creditor identity, name, account details, their bank as provided. The instructed amount, Euro 50,000 for Claudia, never modified after this point. Currency, Euro. Pre-agreed exchange rate if the customer logged one. This goes in layer 1 because the customer decided it, not the bank. Value date mapping to requested execution date. Purpose code when provided. Remittance information, invoice number. Urgency and priority when specified. All of these are sealed at intake. Layer 1 is a pass through to the PAX 8. The values never change from this point forward. Layer 2 is where the bank puts its work. But here is a critical point for part 1. At the end of part 1, layer 2 is entirely empty. Every field you see on screen right now is pending. UETR will be assigned in part 2 after compliance clearance. Settlement method will be determined by the routing engine in part 2. Charge bearer will be determined after scheme rules are applied. Creditor agent BIC will come from the IBAN lookup or name and address search. Intermediary agent BICs will come from the routing decision. None of these values exist yet. If you see any of them populated at the end of intake in your implementation, something has gone wrong with the design. Layer 3 is the engine's working memory throughout the payment lifecycle. Intake timestamp, the moment the canonical was created. Validation status, passed or failed at phase 1. Enrichment status flags, which enrichment steps have completed. Compliance clearance status, cleared, pending or flagged. Routing decision record, correspondent selected, settlement method chosen. Batch metadata, batch ID, position in batch, total count. Retry count, how many times this payment has been reprocessed. Error log, every failure event with timestamp. At the end of part 1, layer 3 has exactly two entries, the intake timestamp and the validation status. Everything else fills in as the payment moves through the pipeline in part 2. I want to address a confusion I have seen in implementation teams. Layer 3 and the audit log are not the same system. Layer 3 is the engine's working memory. It is mutable. It gets updated as the payment moves through stages. It lives inside the canonical. Its purpose is to tell the engine where the payment is in the processing lifecycle. The audit log is a completely separate system. It is immutable. Once a record is written, it cannot be modified. It retains every state transition for regulatory compliance and potential investigation. It is retained for years. Its purpose is to tell a regulator, an auditor, or an investigator exactly what happened to this payment and when. Two different systems, two different purposes. If your implementation conflates them, you will either pollute your audit trail with transient state or lose operational context when the engine restarts. Let me be explicit about the correct canonical state at the end of part 1. Layer 1 complete and sealed. All 9 customer intent elements are in it. It will not change again. Layer 2 empty. Every enrichment field is pending. The enrichment service has not yet run. Layer 3 one entry only. Intake timestamp and validation status. This is the correct state. If your implementation shows anything else populated in layer 2 at this stage, that is where the design went wrong. Now I want to draw the clearest possible line between what the bank must never modify and what the bank must determine. Let me illustrate immutability with the question that trips teams up most often. Claudia submits euro 50,000. Her bank charges euro 5 for the transaction. The creditor bank in Milan charges euro 2.5 to process the credit. What happens to euro 50,000? Nothing. Euro 50,000 does not change. The bank charges euro 5 in separate charge fields. The creditor bank charges euro 2.5 in separate charge fields. Instructed amount stays at euro 50,000 in every scenario. What changes is how much the debtor is actually debited and how much the creditor actually receives. Those are different fields. Charges are not deducted from instructed amount. Let me show you exactly what happens at the euro level across the three charge bearer scenarios. SHAR or SHA. The debtor is debited euro 50,000 plus 5 to cover the bank's charge. The creditor receives euro 49,997.5 after the creditor bank's charge. Instructed amount is euro 50,000 unchanged. Debt or R. The debtor is debited euro 50,750 covering all charges for both sides. The creditor receives the full 50,000. Instructed amount euro 50,000 unchanged. Cred or Ben. The debtor is debited exactly euro 50,000. The creditor receives euro 49,902.5 after both charges are deducted from the received amount. Instructed amount euro 50,000 unchanged. Three scenarios, three different accounting outcomes. One instructed amount, always euro 50,000. And system that modifies instructed amount to account for charges has introduced a bug. Always, no exceptions. To make this visual, instructed amount is a separate locked box. It is marked immutable. It never changes. Below it, calculated separately, is the interbank settlement amount. The interbank settlement amount, which is what actually settles between the banks on each hop. For the SHA scenario, that is euro 50,000. Completely separate calculation. On the side, the bank's euro 5 charge goes into the charges currency and charges amount fields. The creditor bank's euro 2.5 is taken from the interbank settlement amount and not from the instructed amount. Two separate fields even though they are euro 50,000 in this scenario. Two separate accounting entries, one immutable instruction. The accounting works around instructed amount. It never touches it. Here are the primary fields the bank must never modify after intake. Debtor account, legal entity name and their bank. Creditor name, account details and their bank as provided by the customer. the amount, instructed amount, currency, the pre-agreed exchange rate if the customer logged one before submitting, value date, requested execution date, purpose code when provided, remittance information, invoice number in Claudia's case, urgency and priority flag when specified. This is a primary list. In specific payment types and jurisdictions, additional customer provided fields may carry the same immutability obligation. The principle does not change. If the customer provided it as an expression of their intent, the bank does not change it. And here are the primary fields the bank determines. These are the mutable fields. The bank's output, not the customer's input. The creditor agent BIC derived from the IBAN or looked up from name and address. The routing path and intermediary banks. Settlement type INDA, INGA, clearing or COW. The routing engine decides this. The customer never does. The charge bearer, the bank determines this and the scheme may override whatever value the customer provided. The UETR generated by the bank after compliance clearance. The scheme applied to this payment. The and the actual settlement date, interbank settlement date. The customer provided a requested execution date. The bank derives the actual settlement date using the settlement calendar and the cutoff time rules. They are not the same field. Part 2 covers how the bank calculates that date. Here is something most people miss. The content of the backside is not determined by copying pay no one fields one to one. It is determined by decisions that specific pay no one values trigger. Same Claudia, same Euro 50,000, same Italian IBAN. Depending on four key values in the pay no one, the bank can produce two completely different backside messages. On the SEPA SCT path, CLRG settlement, SLE the EV slave charge bearer, a SEPA reachable creditor agent BIC, and a 140 character remittance limit. On the CBPR plus path, INDA or INGA settlement, a correspondent bank selected by the routing engine, different charge bearer logic, and no SEPA remittance length restriction. Same customer instruction, different decisions, different backside. What triggers the fork? Four specific values in the pay no one. Driver 1, the service level code in the payment type information block of the pay no one. If service level contains the code SEPA, SEPA credit transfer rules apply. CLRG settlement method, SHAR charge bearer, the creditor agent must be SEPA reachable. Remittance information is capped at 140 characters. If service level is absent and the creditor is outside a SEPA jurisdiction, CBPR plus cross-border rules apply. INDA and INGA settlement, the routing engine selects the correspondent. Different charge bearer logic applies. The same Euro 50,000 payment to the same Italian bank produces a completely different backset based on this one field. Driver 2 is the currency combination. If the debtor currency, the creditor currency, and the jurisdiction all are domestic RTGS or clearing rules apply. Different settlement infrastructure, different message requirements, potentially a different ISO 20022 message entirely. If the currencies differ or if the payment crosses a country border, cross-border rules apply and the CBPR plus rulebook selection process begins. For Claudia, Euro to Euro and Germany to Italy, different countries but under same SEPA jurisdiction means SEPA rules apply. The currency combination is the first decision node in the routing tree. Driver 3 is whether the creditor account identifier is an IBAN or account number and local clearing code. Claudia provides IBAN present. The bank extracts the creditor agent BIC directly from the IBAN structure. Fast path, clean and automatic. But what if the IBAN or account details is absent? Maybe the customer knows only the name and address of the beneficiary bank. Now the bank must run a name and address lookup. That is slower. It may require manual intervention, and it happens in production more often than implementation teams expect. If your enrichment service assumes every payment will carry an IBAN or account and bank codes, you will encounter surprises in the first weeks of production. Driver 4 is the regulatory reporting field. If regulatory reporting data is present in the PANO 1, it is preserved in layer 1 and passes through to the PAX 8 unchanged. If it is absent but the destination jurisdiction requires it, the bank sets a regulatory data required flag and challenges the payment back to the customer. The bank cannot create the PAX 8 until the data is supplied. This is a pre-PAX 8 blocker, more common in cross-border payments to jurisdictions with strict cross-border reporting requirements. Absence of required regulatory data stops the PAX 8 before it even starts. Four drivers. Service level determines which scheme rulebook applies. Currency combination determines which routing path type to use. IBAN presence or absence determines how the creditor agent is resolved. Regulatory reporting determines whether the PAX 8 can be created at all. These four are the most significant. The full set includes value date versus cutoff timing, account type, correspondent agreement coverage, jurisdiction specific rules, and more. Part 4 covers field level mapping in depth. In part 1, the principle is what matters. Pay no one values trigger decisions. The pack set is the output of those decisions. It is not a copy of the pay in one. Claudia's payment is a single instruction, but banks do not only process single payments. Payroll runs of 500 employees, bulk supplier batches of thousands of invoices, dividend distributions across hundreds of shareholders. All arrive as batches. How the bank handles those batches at initiation matters enormously. There are three approaches. Approach 1 is immediate explosion. Receive 500 payments, decompose into 500 individual canonical instructions. Each has its own independent life cycle. One payment failing does not affect any other. The risk? If you do not tag each canonical with batch metadata, you lose the connection back to the source batch. Approach 2 is keeping the batch as one canonical unit. One canonical instruction for all 500. Do not use this in production. I will explain why in a moment. Approach 3 is the hybrid. Explode into 500 individual canonicals and tag each one with layer 3 batch metadata. Independent processing plus full traceability. This is the recommended approach. Let me show you exactly why approach 2 fails. Payroll run 500 employees. Friday, end of month. The batch is kept as one canonical unit. 3 employees accounts have problems. One account is closed, another has a currency mismatch, the third has triggered a compliance flag requiring manual review. With approach 2, all 500 payments are held until those 3 are resolved. 497 employees do not receive their salary today. The operations team must manually work through the exceptions before anything can proceed. Investigation takes hours. That is operationally unacceptable and it carries real reputational risk for the bank because the failure is visible to hundreds of real people on a Friday. Approach 3 solves this completely. Receive 500 batch payments. Decompose into 500 individual canonical instructions. As each canonical is created, tag it in layer 3 with batch ID, batch sequence, and batch total. 3 instructions fail validation or compliance. They go to the exceptions queues and are investigated independently. The other 497 continue processing without interruption. They do not wait. They do not know about the exceptions. Each has its own canonical, its own life cycle, and its own processing path. The batch ID tag in layer 3 means every canonical can be traced back to the original payroll batch for reporting and reconciliation. 3 exceptions investigated independently. 497 payments processed without interruption. The 3 layer 3 batch metadata fields do most of the operational work. Batch ID ties every individual canonical instruction back to its source batch. This batch ID tells the operations team exactly which payroll run produced this instruction. Batch sequence tells the system this is canonical number 47 of 500. So the complete batch set can be reconstructed if needed. Batch total tells any reporting query how many instructions to expect from this batch. Without batch ID tagging, each of the 500 individual canonicals is independent and anonymous. Batch level reporting requires reconstructing the relationships from external data. That works, but it is harder than it needs to be. The discipline of tagging costs almost nothing at intake and pays dividends throughout the payment lifecycle. There is one more initiation topic to address before we look at the three processing phases, the UETR, and specifically when it gets assigned. UETR stands for Unique End-to-End Transaction Reference. It is UEID4 value. If you have not seen a UEID4 before, it looks like this. Randomly generated, globally unique with a probability approaching certainty. The UETR is the primary key in the Swift GPI tracker. Every bank in the payment chain updates the GPI tracker against this same UETR as the payment moves from debtor bank to creditor bank. One UETR, one payment, all the way from Claudia's bank in Munich to Acme Engineering's bank in Milan. Every bank in the chain sees the same reference. Here is where most implementations get the UETR wrong. The processing timeline runs intake, then compliance screening, then limit check, then other processing gates. The UETR is assigned here after compliance has cleared. After that, the pack set is created. Why does timing matter so much? If you assign the UTR at intake before compliance has run, you are assigning a GPI tracker reference to a payment that may yet be rejected. When compliance rejects that payment, the UTR is now in the Swift GPI tracker pointing to a payment that was never completed. That is an orphaned UTR. The tracker shows a reference with no corresponding successful payment. Regulatory audit questions follow. At volume, this pollutes the tracker and creates significant operational noise. Some sophisticated corporate treasury systems generate UTRs themselves and include them in the Pano one. SAP Treasury does this. Oracle Financials, Kyriba, and FIS also have this capability. When this happens, the bank faces a decision. Option A, trust the corporate UTR and use it. Record UTR source as corporate. The corporate's own GPI tracking stays aligned with the bank's GPI tracker entries. Valid approach. Option B, discard the corporate UTR and generate a bank UTR. Record UTR source as bank and record the original corporate value in original corporate UTR. Also valid. What is never valid is discarding the corporate UTR without recording it. The corporate treasury team may subsequently raise a payment query referencing their UTR value. If the bank has no record of that original value, it cannot link the query to the internal payment record. Trust and discard are both valid strategies. Discard without trace is not. Back to Claudia. At the end of part 1, her Euro 50,000 payment has no UTR. That is correct. Compliance has not cleared yet. UTR is not assigned yet. Exactly right. If you are building a payment system and the UTR is being assigned at intake before compliance has run, that is the implementation mistake to fix before go live. Now, let me pull everything together into the three processing phases that take Claudia's portal submission to an enrichment ready canonical instruction. Three phases. Phase 1 is pre-normalization, the gatekeeper. Anything that fails here never reaches the canonical system. Phase 2 is normalization. This is where all channel diversity ends. Every format, every channel, every encoding converges into one identical canonical structure. Phase 3 is post normalization, the handoff. The canonical is queued for the enrichment service and part 1 ends. After phase 3, the enrichment service in part 2 picks up the canonical and the 5-stage creation pipeline begins. Phase 1 is the gatekeeper. 5 steps run in sequence. Schema validation. Does the incoming instruction conform to the expected format? A malformed JSON, an incomplete CSV, an empty 103 with missing mandatory fields, all stopped here. Authentication and authorization. Is this customer permitted to make a payment request from this channel, and does the submitted authorization match the requirement? Account verification. Does the debtor account exist and is it active? A payment from a closed or frozen account stops here. Format check. Is this a single payment or a batch that requires decomposition in phase 2? Preliminary limit check. Is the amount within the basic transaction limits configured for this channel? At the end of phase 1, if any checks fail, the instruction never enters the canonical system. Phase 1 is the gate that keeps bad instructions out, not a gateway that lets everything through. Phase 2 is where the normalization happens. First, parse the input from its native format. Claudia's HTML form post, a corporate customer's pay no one XML, an ERP system's CSV file, a branch teller's form entry, all parsed from their respective formats. Map all customer provided fields into canonical layer 1. Each field in the channel format maps to its pay no one aligned equivalent in the canonical. If it is a batch, decompose it into individual canonical instructions and tag each with layer 3 batch metadata. Flag any incomplete or missing data that the enrichment service will need to address. Absent IBAN, missing regulatory data, corporate UTR pending decision. Seal layer 1 as immutable. At the end of phase 2, something significant has happened. Claudia's HTML form post, a corporate XML pay no one, a CSV payroll file, a teller form entry has all become identical canonical instructions. The format diversity is gone. Layer 1 is complete and sealed. Layer 2 and 3 are mostly empty. Phase 3 is the handoff. 3 steps. Record the handoff timestamp in layer 3. This is the second layer 3 entry after the intake timestamp. Record the validation status and any enrichment flags. If the IBAN was incomplete, flag it. If regulatory reporting data may be required and is absent, flag it. If a corporate UTR was supplied and the bank has not yet made its trust or discard decision, flag it. These flags tell the enrichment service in part 2 exactly where to focus. Queue the canonical for the enrichment service. That is part 1 complete. The enrichment service in part 2 takes over. For Claudia's Euro 50,000 payment, the canonical is now queued. Layer 1 is sealed. Layer 2 and 3 mostly empty. Ready. 3 phases, 3 distinct outputs. Phase 1 stops invalid instructions before they reach the canonical. Phase 2 normalizes all channel formats into one canonical structure and seals layer 1. Phase 3 records the handoff state and queues the canonical for the enrichment service. At the end of phase 3, part 1 is done. Before we look at the 5 implementation mistakes, I want to make one thing completely explicit about where we stand at the end of part 1. For Claudia's Euro 50,000 payment at the end of part 1, here is what does not exist. UTR does not exist. Compliance has not cleared. Routing decision does not exist. No correspondent has been selected. The chain between Claudia's bank and Acme Engineering's bank in Milan is completely unknown. Settlement type does not exist. Inda, Inga, clearing or cow. The routing engine determines this in part 2. Intermediary banks not identified. If the payment chain requires correspondent banks, we do not yet know which ones. Charge bearer not finalized. A customer preference may have been submitted in the portal. A scheme rule may override it. Neither has been applied yet. Backside does not exist. Not one field has been populated. The message has not been created. What does exist? A canonical instruction with layer 1 complete, layers 2 and 3 mostly empty, sitting in the queue for the enrichment service. If your team assumes anything in that left column exists at the stage of processing, you are building on an incorrect foundation. Now, let me translate every principle we have covered into the 5 specific implementation mistakes I have seen teams make when building payment initiation systems. Mistake 1: confusing format with structure. What happens? The BA says we process pane01 and means the pane01 logical structure. The developer says we use an API and means the transport mechanism. Neither person resolves the confusion. The team builds a parser that is hard coded to handle XML because that is what pane01 means to them. The consequence? A new corporate client sends their payment instructions as JSON with the pane01 structured data. The parser fails. The validator does not recognize the input format. The canonical mapping breaks. What should be 2 weeks of adding one JSON input adapter becomes a 2-month rebuild of the parser, validator, and mapping layer simultaneously. The fix? Separate format, encoding, and structure explicitly in architecture documents from day one. 3 words, 3 definitions, agreed in writing at project starts. Every person on the implementation team should be able to answer what format are we receiving, what encoding, what structure. Mistake 2. Enrichment touching immutable data. What happens? The FX rate has moved between the time Claudia logged her rate and the time the payment processes in the engine. The enrichment service recalculates and writes euro 49,997.50 into the instructed amount field to reflect the actual settlement amount it will be working with. The consequence? There is no longer any reliable record of what Claudia originally instructed. When Claudia requires the payment, the amount shown does not match what she submitted and authorized. When a compliance audit asks for the original instruction, the record shows a modified value. Dispute resolution is extremely difficult. Regulatory inquiries are hard to answer accurately. The fix? Instructed amount is never returned to after layer 1 is sealed. If FX has been applied, the result goes into interbank settlement amount. If charges have been applied, they go into a separate charge fields. The pre-agreed FX rate was captured in layer 1 because the customer decided it. That is the rate Claudia agreed to. Do not touch instructed amount. Mistake 3. All or nothing batch processing. What happens? The payroll batch of 500 payments is kept as one canonical unit inside the engine. 3 accounts have problems. One closed, one with a currency mismatch, one flagged by compliance. The entire batch is held pending resolution. The consequence? 497 employees do not receive their salary. The operations team must manually work through the exceptions before anything can process. This is hours of delay on a Friday at end of month, affecting hundreds of real people at once. The fix. Approach 3. Explode the batch into 500 individual canonicals. Tag each with batch ID, batch sequence, and batch total in layer 3. 3 exceptions go to the exceptions queue and are investigated independently. 497 payments continue processing without interruption. The discipline costs almost nothing at intake. The operational benefit is immediate and pays for itself for the first time. Mistake 4. Sparse canonical design. What happens? The team builds the canonical to handle CBPR plus cross border payments only. It has exactly the fields CBPR plus needs today. Nothing more. It ships and it works well. The consequence, 6 months later, the business wants to add SEPA SCT. SEPA needs fields that do not exist in the canonical. A schema specific service level field, a different charge bearer structure, a capped remittance field. The only way to add them is a schema migration. A schema migration on a shared canonical structure touches every downstream service simultaneously. Compliance, enrichment, routing, posting, audit trail. That is a high risk, high cost program of work that the canonical architecture was specifically designed to avoid. The fix. Design the canonical as a superset from day one. Include the fields for every schema you might plausibly add in the next 3 years, even if most of them are empty today. Empty fields in a well-designed canonical cost nothing. Missing fields cost enormously when the next schema arrives. Mistake 5. Generating the pack set too early. What happens? The development team discovers that generating the pack set early in the process gives them a concrete artifact to test against. So they built it after intake, before compliance has run. A UTR is assigned at the same time to have a tracking reference for the test. It looks reasonable during development. The consequence, in production, compliance runs and rejects the payment. The packsite is discarded. The UTR is now orphaned in the Swift GPI tracker, pointing to a payment that was rejected before settlement. The message ID in the discarded packset is wasted. If this happens at volume, the GPI tracker accumulates orphaned entries and regulatory inquiries follow. The fix: generate the packset only when all five conditions are simultaneously true. 1. Complaints has cleared. 2. Limits have passed. 3. Decisioning has returned approved. 4. Routing is confirmed with cutoff time met. 5. UTR has been assigned. All 5 simultaneously, not before any one of them. If any condition is not yet met, the packside does not exist. 5 mistakes. Confusing format with structure creates hard-coded parsers that break when a new channel arrives. Enrichment touching instructed amount destroys the audit trail of what the customer actually instructed. All or nothing batch processing holds hundreds of good payments hostage because of a few bad ones. Sparse canonical design forces simultaneous engine changes across every service when the next scheme arrives. Generating packset too early creates orphaned UTRs and wasted message IDs in the GPI tracker. All five come from the same root, starting packset thinking at the wrong time in the life cycle. The fix for all five is the same insight we started with. By the time a packset exists, the right work has been done in the right order at the right time. Let me close part 1 with a clear statement of where Claudia's payment stands at the end of this video. Layer 1 complete sealed, 9 customer intent elements preserved exactly as Claudia provided them. Euro 50,000, invoice number, IBAN, all of it locked in. Layer 2 empty, UTR, settlement method, charge bearer, creditor agent, BIC, the intermediary agents, all pending. The enrichment service has not yet run. Layer 3, one entry, intake timestamp, and validation status. That is all. That is the correct state. And this is exactly what the enrichment service in part 2 picks up. Part 1 delivered 5 things. Customer intent captured from Claudia's corporate banking portal across HTML format and pay no one structure. Format diversity normalized. Claudia's portal form, a corporate XML, an XML Excel upload, and a teller form entry all become identical canonical instructions. Layer 1 sealed with 9 intent elements preserved. Batches can be exploded and tagged with batch ID so individual payments live independent life cycles. And the canonical serves as the engine's working horse with all 6 processing services reading from it and writing to it. Part 2 picks up from here with the 5-stage creation pipeline. Stage 1 enrichment, big lookup, scheme determination, compliance deep check, limit validation. Stage 2 decisioning, approve, reject, suspend, or challenge. Stage 3 routing, correspondent selection, settlement type, cutoff check. Stage 4 UTR assignment after compliance clearance. Stage 5 packside generation after all 5 conditions clear simultaneously. That is where the message is born. Thank you for watching part 1. If this was useful, subscribe to the channel and follow Payment Talks at this link. Part 2 is next. How the data agent creates a packsheet, the 5-stage pipeline, the pay no one to packsheet derivation chain, the interbank settlement amount derivation. That this is where we watched Claudia's canonical become a network message for the first time. See you there. Until then, keep learning, keep smiling. Thanks for watching this video. If you like this video, please like, subscribe and share for more such interesting topics on payments.